So I had a couple recent videos where people in the comments pointed out that we could have also found a solution to these problems using something called the Stolz-Cesaro Theorem. And so I wanted to make a video of that to give myself an opportunity to brush up on that theorem. And so this is sometimes thought of as the discrete L'Hopital's rule. And so let's look at the statement here. So I want to do this all in terms of something called the discrete derivative or the forward difference operator. So let's define that first. So if you've got a sequence an, then delta an, so that is the forward difference operator acting on an, or the discrete derivative of an is an plus 1 minus an. And then we can state this theorem. So if we suppose that an and bn are sequences and bn is monotone, then we have two cases. If the limit as n goes to infinity of bn is plus or minus infinity, and the limit as n goes to infinity of delta an over delta bn, you want to think of this as like the derivative of the sequence an and the derivative of the sequence bn. But in sequence world, the derivative is, like I said above, given by this forward difference operator. So if that limit equals L, then the limit of just the quotient of the two sequences also equals L. So recall from L'Hopital's rule, over here we would have the limit of the quotient of derivatives and the limit of just functions. The quotient of functions, I should say. And then the other case is like our 0 over 0 case. So if the limit as n goes to infinity of an is the same thing as the limit of bn, and that's 0, and the limit of delta an over delta bn is L, then the limit of the quotient an over bn is also L. Okay, great. And then another thing that I want to recall here is sometimes called the discrete fundamental theorem of calculus, or the fundamental theorem of discrete calculus. And that says if you sum from k to r of s of delta an, and that should be delta ak, then you get as plus 1 minus ar. And so compare that with the regular fundamental theorem of calculus that says if you integrate from a to b of f of x dx, or maybe you should say the derivative of f of x dx, what happens? And so the same thing is happening here, except our integral is replaced with a sum, and our regular derivative is replaced with this forward difference operator, or this discrete derivative. Okay, so I want to look at a proof of this first case, and the second case will follow like similarly, or maybe even as a corollary of the first case. I'll let you guys think about that. Okay. So what we want to do is suppose that an and bn are sequences kind of satisfying the hypotheses that we need over here, where we have this monotonicity, but bn is going to infinity. Something similar would happen if bn was going to a negative infinity. So in other words, we have bn plus 1 is bigger than or equal to bn. That would be it's monotonically increasing. And the limit of the bn terms is positive infinity. Okay, good. So now what we're assuming here is that this limit right here exists. So in other words, the limit as n goes to infinity of delta an over delta bn equals L. So this exists and is finite. Great. But by the precise definition of a limit, that means that for any epsilon bigger than 0, there exists some natural number n such that delta an over delta bn minus L in absolute values is less than epsilon, and that's going to be true for all n bigger than or equal to this special n. Okay, but now I want to rewrite this a little bit. That's the same thing as saying the following inequality. So L minus epsilon is less than delta an over delta bn, which is less than L plus epsilon. And like I said, this is for all n bigger than or equal to n. So now from here, what I want to do is clear the fraction in the middle. So I'll multiply it by this delta bn. That's going to give me delta bn times L minus epsilon is less than delta AN, which is less than delta BN times L plus epsilon. Okay, so that's where we are. I'm going to go ahead and bring that up, and then we'll continue on. Okay, so we left off with this fact. For any epsilon bigger than 0, there is a natural number n such that delta Bn times L minus epsilon is less than delta An, which is less than delta Bn times L plus epsilon. Now, the next thing that I want to do is I want to sum, and I should say, that is for all n bigger than or equal to this capital N. Now, the next thing that we're going to do is take advantage of the fact that this inequality is true for all n bigger than or equal to capital N, and then we're going to sum over some values of n that are bigger than or equal to capital N. And those values are going to be n running from capital N up to an arbitrary value k. Okay, so let's see what we get when we do that. So we're going to have L minus epsilon times the sum equals little n to k of delta Bn. So that's what we get for this left-hand term. Notice I've factored this L minus epsilon out because it doesn't depend on our index. And now that's going to be less than the sum n equals capital N to k of delta An, which is less than L plus epsilon times the sum n equals capital N to k of delta Bn. Fantastic. But now we can apply this discrete fundamental theorem of calculus. I have a proof where we prove this theorem and do some examples with it. I'll link that in the description. And so that's going to allow us to simplify this quite a bit. So that's going to leave us with L minus epsilon. And then notice we're going to have one more than the upper bound minus the lower bound plugged in. And so that's going to give us B k plus 1 minus Bn. So that's what we get there. And then here we're going to get ak plus 1 minus a sub n, and that's capital N. And here we're going to have L plus epsilon, and then bk plus 1 minus b capital N. Now we're going to look at this inequality and notice it's mostly made up of constants. Notice that L is a constant, epsilon is a constant that has been fixed above. Capital N is a constant which depends on epsilon. That makes B sub capital N a constant, A sub capital N a constant, and then this B sub N a constant as well. So let's go ahead and underline everything which is like a constant. And then the b sub k plus 1 is like a variable. Notice here we can vary this k larger or smaller. Probably larger because we're going to eventually want to take a limit. So let's go ahead and circle everything in here that's kind of like variable still. In other words, it depends on something that's like a variable. In this case, the index k. Okay. So the next thing that we want to do is try to consolidate those terms which are variable into one part of the inequality. And we can do that by dividing by this bk plus 1. So let's go ahead and divide by this bk plus 1 and see what we get. So that's going to give us L minus epsilon here. Then we're going to have 1 minus b sub n over b sub k plus 1. Fantastic. And here we're going to have a sub k plus 1 over b sub k plus 1 minus a sub n over b sub k plus 1. And then finally here we're going to have L plus epsilon and then 1 minus b sub n over b sub k plus 1. Now we're actually in a really good spot because we know that bk plus 1 will trend to infinity. Remember, that was one of our assumptions, which means as k goes to infinity, this term right here is going to go to 0. So let's talk our way through that. So how do we know that that goes to 0 as k goes to infinity? Well, recall b sub n is a constant. So it's a constant that depends on this n that we plugged in, but that n is fixed by our original choice of epsilon. Great. And so likewise, this term right here is also going to go to 0 as k goes to infinity. And this term over here is also going to go to 0 as k tends towards infinity. for all of the same reasons. So notice we have some sort of squeeze theorem thing happening. Notice we have an L minus epsilon over here on the left-hand side, which is less than the limit as k goes to infinity of ak plus 1 over bk plus 1, which is less than L plus epsilon. So just to reiterate, we've, in a sense, applied the squeeze theorem to this inequality in order to get this. We've taken the limit of the first portion of the inequality, the middle portion, and the second portion. But now we see that this inequality is true for all epsilon bigger than 0, because up here we chose an arbitrary epsilon. But whenever inequalities are true like this for all epsilon bigger than 0, we know that our limit is exactly equal to L. Okay, great. And that proves the first case of this theorem. Okay, great. I'm going to clean up the board and we're going to apply this to some recent results from previous videos. Recently I did a video on the Putnam problem B4 from the year 2012, and after stating and proving this Stolz-Cesaro theorem, I want to give another solution to this problem using this nice theorem. Okay, so let's see what it says. We suppose that a0 is 1 and an plus 1 is an plus e to the minus an for all n bigger than or equal to 0. And the question is, does the limit as n goes to infinity of an minus natural log of n exist, and is it finite? And we'll actually show that yes, it exists, it's finite, and we will find the value as well. Okay, before we get to the point where we can apply this theorem, we're actually going to notice something, and that is that an is increasing. And that's pretty easy to see because an plus 1 is strictly bigger than an. And again, that follows from the fact that e to the minus an is bigger than 0. So let's go ahead and put that in here. So that's because e to the minus an is bigger than 0. But what that tells us is that e to the minus an is decreasing. And so that's pretty easy to see. If an is increasing, then e to the minus an is decreasing. And that's because e to the minus x is a decreasing function. So good. But what that tells us is that the very, very first value of e to the minus an is the largest. So we have e to the minus an is in fact less than e to the minus a0, which is e to the minus 1. And so that is 1 over e. Okay, great. So now let's get going with calculating this limit, and we're going to do that by using this theorem. And so the first thing that we want to notice is that our limit, so let's just go ahead and say that our limit is this limit right here, and we'll use the word okay for existing and being finite. So we'll say is okay, and then let's just point out that by okay we mean it exists and is finite. If and only if, when you exponentiate this limit, it also exists and is finite. And that's because, again, e to the x is a continuous function. And so let's exponentiate this. So that's e to the an minus natural log of n. Now, I want to motivate why we did that. And so our goal is to use this theorem, but notice this theorem has something to do with quotients of sequences. And so somehow we need to turn this difference of a sequence into a quotient of a sequence, and we can do that via exponentiation. Because notice, when we exponentiate here, we can use our exponent rules and the fact that e and natural log cancel to immediately change this to the limit as n goes to infinity of e to the an over n. Great. And so our limit is okay if and only if this limit is also okay. Great. But by this theorem over here, this limit is okay if and only if when we apply the discrete derivative, in other words, the forward difference operator to the numerator and the denominator, we also get a limit that's okay. And so let's say this is if and only if the limit as n goes to infinity of delta e to the an, over delta n is okay. And then let's just recall, by okay, I mean this thing exists and is finite. So now our goal is to find this limit, but notice if we find this limit, it will have the same value as this limit, which is equal to this limit. But this limit is just the exponential of our original limit, and so we'll tie all that up at the end, but we can actually use that to calculate our very original limit. Okay, great. So now let's go ahead and calculate the forward difference operator to the numerator and the denominator. So that's going to give us the limit as n goes to infinity. We have e to the a n plus 1 minus e to the a sub n over n plus 1 minus n. Great. So again, that's applying the discrete derivative or the forward difference operator. But the next thing that we can notice is that this is going to be the limit as n goes to infinity. The denominator is super simple. It just becomes 1. And then for the numerator, we can use this recursion in order to rewrite e to the a n plus 1. So that's going to allow us to write e to the a n plus e to the minus a n. And this is going to be minus e to the a n. Okay. Fantastic. But we can factor this term out, and notice when we factor this, it's actually pretty nice. We can write this as e to the a n times e to the minus a n. But that's going to allow us to write this limit as the limit as n goes to infinity of e to the a n times e to the minus a n minus 1 after factoring out that e to the a n. All right, great. So the next thing I want to do is move this up, and we will continue calculating this limit. So we just argued that our original limit is okay if and only if this limit as n goes to infinity of e to the a n times the quantity e to the minus a n minus 1 is also okay. All right, so let's see how we can use that to our advantage. Well, what we want to do is use a Taylor expansion of this guy right here. And so, in fact, we'll want to use the fact that e to the u equals 1 plus u plus u squared over 2 factorial plus dot dot dot, and here u is going to be e to the minus a n. All right, great. So notice the 1 terms will cancel because we've got 1 from each. And then we're going to be left with a bunch of other stuff. So let's see what we get. So that means this limit right here is going to be the same thing as the limit as n approaches infinity of e to the a n. That's outside. And then the first term inside is e to the minus a n. Great. And then the second term inside is e to the minus a n squared over 2 factorial plus e to the minus a n cubed over 3 factorial plus dot dot dot. Now the next thing that I want to notice is that this guy right here, I can factor an e to the minus a n squared out of it. So let's go ahead and do that. This is going to be the limit as n goes to infinity of e to the a n, and then we have e to the minus a n plus e to the minus a n quantity squared. And then we have all of this stuff left over. And so let's see what this stuff left over is. That's going to be 1 over 2 factorial plus e to the minus a n over 3 factorial plus dot dot dot. Great. But the next thing to notice is that this looks a lot like our original series, except we have rescaled all of the terms, which is going to make it smaller than our original series, because our original series, in other words, the expansion of e to the minus a n, has bigger coefficients for all of the e to the minus a n terms. So, just to reiterate, all of this right here is going to be less than or equal to e to the minus a n. Great. But another thing that we can notice is that e to the minus a n is less than 1 over e. So this whole thing is less than e to the 1 over e, which is just a constant. So now I want to simplify this a little bit. So multiplying this e to the a n through, that's going to give me the limit as n goes to infinity of 1. So that's what I get from this e to the a n term. And then multiplying this e to the a n through to this e to the minus a n squared, I get plus e to the minus a n there. And then the next thing that I have is this term right here, which I can put all together into something maybe called x sub n, where all of those x sub n's are bound above by e to the 1 over e. So I'm going to go ahead and call this x sub n right here. Great. Now I can go ahead and take the limit as n goes to infinity. I know that this thing right here is going to be bound by 1 over e, and then a n goes to infinity. So we didn't check that, but that's going to follow pretty simply from this increasing nature and kind of the structure of a n in the first place. But that means e to the minus a n is going to approach 0. So we have something approaching 0 multiplied by something that is bound, so that whole thing's going to go to 0, and that gives us our limit of 1. Okay, great. But if our original limit up here is equal to y, notice we gained this by exponentiating, so that means we have e to the y equals this thing right here. But that means down here we have e to the y equals 1. In other words, y equals the natural log of 1, which is 0. So y is equal to 0. So yes, this limit exists and it's finite, and in fact we know its value is equal to 0. Okay, so that's a good place to stop with this problem. Now I'll clean up the board and we're going to do another problem that we've recently done using this theorem. Okay, next we're going to revisit this limit, which we found in a previous video using Riemann sums, but we're going to use this forward difference operator and the Stolz-Cesaro theorem. In other words, the discrete L'Hopital's rule. So that means we can take the discrete derivative, in other words, the forward difference operator of the numerator and the denominator, to simplify this. So let's go ahead and do that. So if we take the forward difference operator of that and the forward difference operator of that, then as long as the limits exist, which in this case we're going to assume they exist, so we're going to cheat a little bit, we should have the same value. So let's see what we get when we do that. So that's going to give us the limit as n goes to infinity. Now let's see what we have in the numerator. We're going to have 1 to the a plus 1 plus all the way up to n to the a plus 1 plus n plus 1 to the a plus 1. So that's what we get if we plug in n plus 1, and then minus the original, which is 1 to the a plus 1, all the way up to n to the a plus 1. Good. And then in the denominator, we're going to have n plus 1 times 1 to the a, all the way up to n to the a plus n plus 1 to the a, minus n times 1 to the a, all the way up to n to the a. Okay, fantastic. So let's see what we get. In the numerator, a bunch of stuff is going to cancel. This 1 to the a plus 1 and this 1 to the a plus 1 all the way up to this n to the a and this n to the a are going to cancel. And that's going to leave us with the limit as n approaches infinity. In the numerator, we have n plus 1 to the a plus 1. And now let's see what happens in the denominator. Not as much stuff will cancel, but still a lot will. So notice we'll have n plus 1 times these first terms minus n times these same first terms. So that's going to give us n plus 1 times this minus n times this. In other words, 1 times that. So that's going to be 1 to the a plus 2 to the a all the way up to n to the a. Okay, good. And then we're going to have n plus 1 times n plus 1 to the a. In other words, that's going to be n plus 1 to the a plus 1. Now the next thing that we want to do is apply this forward difference operator again. So let's see what we get when we do that. So applying this thing again, so let's say SC for this theorem, that's going to give us the limit as n goes to infinity. So we're going to have n plus 2 to the a plus 1 minus n plus 1 to the a plus 1. That's what happens in the numerator. And then in the denominator, well, I'll let you guys check carefully, but these guys are going to simplify a lot, and that's actually kind of the beauty in all of this, is that these big sums simplify a lot when you apply this forward difference operator. And then in the denominator, you're going to get n plus 2 to the a plus 1 minus n times n plus 1 to the a plus 1. Okay, fantastic. Now the next thing that we want to do is expand everything in the numerator and the denominator as a binomial and keep the leading terms. You just have to be careful about how you're expanding it in terms of where are you expanding it about. So notice, since we're letting n go to infinity, you actually want to expand this in a neighborhood around infinity. So in other words, in terms of infinitely many powers of n that are negative. Okay, so let's see what we get when we do that. So in the numerator, we're going to have the limit as n goes to infinity, and then we're going to have n to the a plus 1 plus 2, a plus 1 choose 1, n to the a plus lower. So again, that is going to be this first term right here. Great. And then notice the second term will have minus n to the a plus 1 plus a plus 1 choose 1 n to the a plus lower. And that is going to be this second term. Okay, good. And then let's go ahead and see what we have in the denominator. So this term is going to be exactly the same. So we're going to have n to the a plus 1 plus 2, a plus 1 choose 1, n to the a plus lower order terms. So that's the same as this one right here. And now this one is pretty similar. Oh, except I see there's a typo here. This should be just n to the a. So this is going to give us minus n to the a plus 1 plus a choose 1 n to the a plus lower. Because notice we're expanding with an 8th power instead of an a plus first or an a plus second power. So again, that is going to be this term right here. Okay, so now let's see what we get after everything cancels. So that's going to give us the limit as n goes to infinity. And then in the numerator, these top two terms are going to cancel, and we're going to be left with 2 times a plus 1 minus a plus 1. So notice a plus 1 choose 1 is just a plus 1. Same thing over here, and that is going to be our coefficient of n to the a plus lower order terms. And then that's going to be divided by, well, notice that this n to the a plus 1 and this n to the a plus 1 term are going to cancel, and we're going to be left with 2 a plus 1 minus a. Again, that's because we have a plus 1 choose 1 is a plus 1, and a choose 1 is a, and that's going to be multiplied by n to the a plus lower. Fantastic. Now we can just use our rule about finding limits of rational functions or rational-like functions. If the degree of the numerator and the denominator is the same, then your final limit is the quotient of that leading coefficient in the numerator divided by that leading coefficient in the denominator. So let's see what we get. We have twice a plus 1 minus once a plus 1, so that's going to give us a plus 1 in the numerator. And now we have 2a plus 2 minus a, so that's going to be a plus 2 in the denominator. Great, and that's going to finish off this video.